Without further ado, let's start with our first speaker, Javier Ideami, CEO of Ideami, co-founder of Geniverse, and a visionary at the intersection of art and AI. Today, he'll be taking us through the 7 rings of AI, what we've achieved, what we haven't, and what comes next.
All right, let's go. Thank you. Good morning, everybody. Good morning, everybody. Oh, we got a microphone. This will be helpful. Okay. Good morning, everybody. Can you all hear me well? Fantastic. Well, it's wonderful to be back 1 year later. Thank you, Minsky, Jack, DevelopMetrics, for inviting me to be back here with the talk that is called The 7 Rings of AI. 7 rings for the machines in the land of humans. Forged in Dartmouth in 1955. 7 tasks to bind intelligence. And many different visions to try to unite them, and 1 ring to rule them all. AGI, Artificial General Intelligence. So what is this talk about? Let's see. Let's put this here. Okay, the 7 rings of AI. And 1 ring to rule them all. So, we are all excited because artificial intelligence is already producing a lot of benefits and good results in all kinds of sectors. But of all the sectors where we can apply AI, development is one of the sectors that requires a series of features, some of which are not yet completely with us, right? Because we know that in development, you are all dealing, and we are dealing with all the complexity of humans, a lot of dynamic contexts, a lot of change, resources and infrastructure that changes very fast, a lot of uncertainty, unpredictable events, multiple stakeholders, a lot of nuances and subtleties, long and short-term impact that is very dynamic, and a lot of interconnected systems, education, health, environment, etc., etc. And this, ideally, would require, right, a kind of AI that could be what? Explainable, interpretable, adaptable, flexible, trustworthy, that would have a robust causal understanding of the world, that would be able to extrapolate beyond its training distribution, that would be able to do continuous learning to adapt to new scenarios. And all of these features are very connected to what we typically define as AGI, Artificial General Intelligence, the type of machine intelligence that is at the level of humans. So the question is, beyond what AI is doing in development today, all the predictive analytics, the beginning of some generative stuff, we want to look towards the future to see when we will have that kind of AI that will be ideal for the field. So how do we get a realistic view of how far we are from that? And you see, when we mention that some of those features are not yet here, sometimes we are told that we are moving the goalposts, right? We say, oh, AI has achieved something, and they say that we are maybe redefining what intelligence means. So how can we get a realistic view beyond the hype, beyond the fundraising, that does not move the goalposts? So this talk is about doing a little bit of time travel so that instead of shifting the goalpost, we are going to go back to the original ones. And we're going to do a little bit of time travel, because in the summer of 1955, 70 years ago, that's why it's beautiful that we do this talk today, because, you know, if it was 71 or 72, it wouldn't be so nice, right? But it's 70 years ago. This is the right year to do this talk. 70 years ago, a small group of scientists, some of the greatest geniuses in the history of computing science, they wrote 7 things, 7 rings, 7 things that machines would need to do if they were ever to be called intelligent at the level of humans, at that level that ideally the development field will need in the future. That moment is considered the birth of AI. Notice that these 7 rings, they have different sizes. Today, some of these rings fit better or worse in our projects. And we are now going to find out, and you see what we're going to do in this talk, you will be able to use it after this talk when you debate with people how far you are from the ideal kind of AI that the development field needs. You will be able to use the content of this talk. So we're going to do a bit of time travel. Did they tell you that in this talk we were going to do time travel? They didn't, right? Okay, too late now. You are already in the time machine. So we're going to do time travel, ladies and gentlemen, to 1955 to see which one of those 7 rings today fits well or not so well with our development projects. Let's go to August 31st, 1955. Are you ready to start the time machine? Are you ready? Are you ready? Really? I don't hear anything. Are you ready? Yes. Let's crank up the time machine. Welcome to 1955. It's a beautiful summer. And this is a proposal for the Dartmouth Summer Research Project of Artificial Intelligence by McCarthy, Minsky, Rochester, and Shannon, some of the greatest geniuses in the history of computing science. All right. And this is what these geniuses proposed. They said, you know, we believe that in 2 months, in the next summer, in the one of 56, with 10 people and $13,000, equivalent to $160,000 of today, we believe we can make great progress in these 7 points. And here we are, 70 years later. All right. So let's see what is the situation 70 years later. And what I'm going to show you is I'm going to show you each of the points at the top in the written in the academic jargon, and in the center of the screen, I'm going to put the gist of it summarized, okay? And we're going to evaluate each of them. But before we do this, before we really enter the time machine, I'm going to ask you to do something in 15 seconds that will be very fun at the end of this talk. I want you to write down on your mind or on your mobile phone or on a paper a number from 0 to 100 of how far you think we are today from that ideal kind of AI that would be perfect for the development field, from that AGI. So note on your mind or on your phone or whatever you want, a number from 0 to 100 of how far you think we are, okay? 10 seconds. Don't think about it too much, just use your intuition. I'm not giving any hint, just whatever number, okay? Okay, raise your hand if you have a number. Yeah? Everyone has a number, great. Let's begin. Point number 1, automatic computers. At the top is the academic jargon. In the middle, the gist. Computers can, in theory, simulate anything, even intelligence. The biggest challenge is not hardware, which will eventually be solved, but figuring out the right programs, the software on top. So, this is about hardware and software. And in 1955, 70 years ago, they were aware of their hardware limits, but they still saw that the main challenge was finding out the right software on top. So 70 years later, hardware is no longer the bottleneck. We use compute plus training to learn the programs, that are the neural networks, instead of handcrafting them. Now, this works very well for System 1, fast thinking, pattern recognition, but it's still falling short of robust causal reasoning and true understanding. We're only beginning the System 2 slow thinking era. So we solved the hardware compute side, but we have not figured out fully the software side of it. We are working with optimization, right? Gradient descent, backpropagation, a bit of reinforcement learning, now a lot of in fashion. But the deepest form of causal, robust reasoning are still elusive. So we're going to give it a 60% because hardware is pretty much there, although it's very inefficient, still very far from the 20 watts that our brain uses in efficiency. But the software side, only with gradient descent and with reinforcement learning, we are not going to get all the way to AGI. We're still going to need improvements in algorithmic systems and in architectures. So, point number 2, how can a computer be programmed to use a language? The gist, can a computer learn to understand, to use human language? So this is about human language, and 70 years ago, they saw language as central to human thought. Would you agree that language is central to human thought? Yes, I think we all agree, okay? But they saw no clear way to formalize that or implement it. Now, 70 years later, LLMs are doing great, right? They show that machines can use and generate human language with great fluency. Yet, they still struggle with grounding, with deep reasoning and true causal understanding beyond the patterns of text. And so we solved in a way the Turing test of machine language, at the surface level, but deep reasoning, grounding, and true understanding remain open challenges. This is why, you see, hallucinations are not a problem, because we humans also hallucinate, out of the combination of our input, our perception, and our world model. And machines hallucinate when the prompt and the latent spaces go out of sync. The problem is that LLM hallucinations are more unpredictable and often also more silly because they don't have a robust causal understanding of the world. So we're going to give them 80% because we have done great with the language, okay? But we are still dominating it in a way at the surface level. Okay, point number 3, neuron nets. The gist, if we connect artificial neurons together, could they learn concepts like a brain does? All right, so 70 years ago, they started to do some early experiments with neuron nets. They were very simple, but promising. And 70 years later, of course, deep neural networks dominate AI, from vision to LLMs. They clearly can learn useful abstractions and approximate concepts, but we still don't fully understand how they represent meaning, and interpretability remains a challenge. You know, the field of, okay, how many people here are aware of a field in AI called mechanistic interpretability? Raise your hand. There's only one. Okay, that tells you everything you need to know about how early we are in that field of AI, in which Anthropic, the company Anthropic, has been doing a lot of great work. But people are still very confused. There's only one person here who is aware of this field. So you just search for mechanistic interpretability. You see, it's actually quite a huge field, but it's only beginning. Okay, so in summary, we validated a neural net vision, but challenges remain. How to optimize the way concepts are represented. This will be very interesting in point number 6. In the latent spaces, how to interpret them and how to align them with human values, of course, alignment. Okay. So we're going to give them 80% because, yeah, we validate the neural networks, but we have still to refine a lot of things. Okay, we are approaching points number 5 and 6 and 7 because you will see that points 5, 6, and 7 are going to be absolutely fascinating and very surprising. Let's go to point number 4. Theory of the size of a calculation. How do we measure if a problem is too big or too slow to solve? And how do we solve it more efficiently? You see, we are dealing with all types of problems. They needed a theory of complexity, and they needed a way to know how to be efficient solving those problems. So 70 years ago, it's beautiful, 70 years ago, it's just such a round number. Okay, so they recognized that brute force is inefficient. AI needed a way to judge efficiency and complexity, but formal tools were just emerging. 70 years later, we have complexity theory, efficient algorithms, and heuristics. But we are mainly using approximations, right? A lot of pattern matching, some search, like Monte Carlo tree search algorithms and others, and lots of scaling to tackle enormous problems. Still, many systems are leaning heavily on raw compute rather than true efficiency. So we've built strong foundations for measuring and improving efficiency, but in practice, many modern AI breakthroughs rely on brute force scaling. This is starting to change now, rather than elegant, efficient solutions. Again, we're very far from the 20 watts of power that the human brain is using. So we're going to give it 70% because we've done great with complexity theory and with scaling as well, but efficiency is still missing. Okay, now we arrive to 5, 6, and 7. We've done quite well with 1, 2, 3, 4. Now, I just want you to remember something very important now. Points 5, 6, and 7 are goalposts that were not proposed last week. They were not proposed 1 month ago. They were not proposed 1 year ago. They were proposed 70 years ago. So when you interact with hypers or whatever, and you have a debate about this, tell them points 5, 6, and 7 were proposed 70 years ago. Point number 5, self-improvement. Gist, could a machine get better on its own, improving itself without us reprogramming it? 70 years ago, they saw self-improvement as essential to true intelligence, but had only abstract ideas. They are even celebrating. Point number 5 there. 70 years later, today's AI learns during training, but once deployed, it is frozen. Tell me one thing, for the development field, is it positive that we have frozen models when we deploy them in inference? Is it positive? No. We are looking to solve that, right? Okay. They are unable to continuously adapt, truly learn from its environment, redesign their own goals and architectures. So we gain powerful training methods, but open-ended self-improvement, machines that keep learning and evolving, remains unsolved. Now, there is a benchmark called ArcAGI. Who is aware of the ArcAGI benchmark? Raise your hand. Okay, we have a few people. So this is a benchmark created by François Chollet that is challenging machines to solve problems with only a few examples, like we humans do. You know, we have played, for example, a number of games. If I now show you a new game, and I just show you very few examples of how to play it, you will be able to play it in no time. So this is a sort of benchmark, and in this benchmark, in the new version number 2, the best models of the top companies do not go beyond 15 or 20%, okay? And even using a lot of brute force. So, now, in the last year, we have seen the rise of some techniques like test time training and test time fine-tuning. What these techniques try to do is that when you deploy an AI model in inference and they find something new, they sort of can do like a fine-tuning with a few examples of that new scenario that they find. They can do a fine-tuning during inference to try to adapt to that new scenario. This is just like a very, very little, sort of brittle, hacky beginning to try to solve this. Just like a very little beginning, okay? Now, I want to make you aware that there are other alternative paradigms to the current dominant one. And last year, I spoke about one of them, active inference. Okay, these are alternative paradigms that are trying to create a different type of AI that from the very beginning is going to be able to continuously update its probabilistic world model and sort of self-improve itself and with robust causal understanding and in a very adaptable way and in a probabilistic way. And this is active inference, one of these frameworks. There is, for example, that is being pushed by this company called Versus. And I spoke about this last year, and what time is it? Let me check the 10 minutes only. No, we need more. Okay. let's rush, let's do it. We can do this. Okay, so Versus is pushing active inference, and then we have Liquid AI, who is using physics, basically physics, to try to also create a type of AI that is way more fluid, more adaptable, okay? So we're gonna give it, and then Rich Sutton, the founder of reinforcement learning, is talking about the era of experience. Right now, we're living the era of data. We take all the data of the internet, we have the AI entity, and we try to cram all the data into the metaphorical mouth of the AI, and we say, please learn everything. And he's talking about the era of experience, that is the next era of AI, where we will have AI agents that interact gradually with the complexity of the world, and in a modular, hierarchical, elegant way, they build robust causal abstractions gradually, okay? The era of experience. So we're gonna give it a 40%, but we're still pretty far. Now, point number 6, abstractions, the gist. Can machines form higher level ideas and concepts from raw data, like humans do? This is huge, my friends, because, you see, a machine and a human, they can both give the right answer to a problem. But just as important as the answer is how do we get to the answer? Do we get to the answer like Professor Kenneth Stanley tells us in this academic paper? Do we get to the answer by cramming all of that data all at once into an AI entity so that it creates this sort of fractured, messy, entangled set of representations in which each neuron is connected to a million things and it's impossible to interpret or explain anything? That's one way. Or do we build gradually an elegant, modular, hierarchical, clean set of abstract, compressed abstractions that are easy to interpret and explain and work with and manage? So in this beautiful academic paper, Kenneth Stanley and his team, they actually demonstrate that with evolutionary algorithms, they can build that sort of clean, elegant set of abstractions in contraposition to the current ones that are used in AI. So there is a lot to change yet in this area. So 70 years ago, they wanted machines to form abstractions from data and sensory input, as we do, but they didn't know how to do it. 70 years later, neural networks learn rich latent features, indeed, that look like abstractions, indeed, but they are often brittle, they lack causal grounding, and don't build modular hierarchical world models like humans. True flexible abstraction is still missing. So machines can represent useful features that act like abstractions, but robust causal hierarchical abstractions, the kind humans use to reason flexibly about the world, remain unsolved. This is a huge, huge one, and we're going to give it 40%, therefore. And we go to the last point. Point number 7, randomness and creativity. the gist of it. Is creativity just smart randomness? And can a machine be truly imaginative? This is very, very relevant for the development field. I will tell you why. In 1955, they thought that creativity comes from injecting randomness guided by intuition. 70 years later, we are all amazed with generative AI, in which I have worked very much and I have co-founded startups in the field. With its creativity within its training distribution, but struggles to extrapolate beyond it or generate truly novel concepts. So we built powerful interpolators, but open-ended out-of-distribution creativity, the kind humans used to invent, and the kind development projects need to use to adapt in real time to unforeseen and unpredictable and unexpected changes in scenarios remains unsolved. And you know, I think a lot of us, at least I have, like, at the same time that I celebrate generative AI because I work in generative AI and I have co-founded companies in the field, at the same time I have hundreds of very silly examples of when you try to ask one of these models to extrapolate beyond its training distribution, and it's just, they are hilarious, basically. Okay, so we're going to give it 50% because they are amazing. Generative AI is amazing, but we still have a lot to solve. So what is the final result? So the average of everything, ladies and gentlemen, the average of everything with these goalposts proposed 70 years ago is 60%. Okay, how many of you had a number that was less than 60%? Raise your hands. Less than 60%, and now more than 60%. Ooh, it's almost, okay, again, less than 60%. Okay, and now more than 60%. Is very close to a tie, but I would say maybe a little bit more, less than 60%, which is very nice because in the last months, there is a gradual move towards that. I think since the launch of some of the latest models, people have started to realize that, okay, maybe AGI is not 4 months away, you know? Maybe it's not 4 months away. Now, I'm going to show you something very interesting. Only 1 week ago, this is a complete coincidence, some of the greatest minds in AI, they published a paper that went viral, precisely answering the same question, okay, but using goalposts proposed like last week, basically, in the last months. So, do you know what is the result? You know what is the result? What is the result comparing the state of the art, that is GPT-5? 58% is the same result. Okay, 60%, 58%. These people got to basically the same number. Okay, but using goalposts that they thought about in the last months, you know, instead of using the original ones from 70 years ago. So what this means is that pretty much we are on target, right? So what this means is that we have made remarkable progress in the last 70 years, much more than the pioneers of 55 could have imagined, but we're still far from AGI. Many of the hardest problems, continuous self-improvement, robust abstraction, causal reasoning, true creativity, extrapolation remain unsolved. And now the end of the talk, for which I have the amazing amount of how many minutes? No, 5 at least. You have to give me 5. 5. Okay, 5 minutes. So, very important because it's now when you bring it all together in your hippocampus, okay? So, what has happened in the last 70 years is that 5 different tribes, the connectionists, symbolists, evolutionaries, bayesians, and analogizers, have been trying to solve the AGI problem from different perspectives. The connectionists, that is the dominant paradigm today, deep learning, you know, they are working with data, they are learning patterns at scale, great for pattern matching, but they are very data hungry and they are very brittle outside the training distribution. Now, the symbolist is all about working with rules and logic, and you know, they are very precise and they are very explainable, but they are very rigid and they fail outside of their narrow domain. Now, the evolutionaries, they use genetic algorithms and they can explore vast solution spaces creatively, but they can be slow, unpredictable, and resource intensive, and they can get stuck in local minima. Now, the Bayesians, probabilistic, you know, they deal very well with uncertainty, but they are hard to scale, and they use a lot of simplifying assumptions that limit them. And finally, the analogizers, about metaphors, analogies, they work with similarity, they are very intuitive, they leverage past examples directly, but they don't generalize well beyond seen cases. Now, what has happened is that in the last 70 years, these 5 ways of trying to get to AGI, they have not only used different strategies, but almost fought with each other. The future is in combining these tribes. and we are already seeing the beginning of it with neurosymbolic systems. Like, for example, AlphaFold from DeepMind, the system that predicts the structure of proteins. That is a neurosymbolic system that uses deep learning and neural networks, but also symbolic modules that sort of constrain and refine the approximations of the neural networks. And we see a lot of rise in academic papers and efforts in neurosymbolic approaches. And as I told you before, also in alternative paradigms like active inference and the like. But even those are not going to succeed in 2 days, okay? Because neurosymbolic is great. It combines neural flexibility with symbolic precision, but they are hard to integrate, and learning the rules of the symbolic modules is a big challenge. And active inference is a unified framework for perception, action, and learning under uncertainty, but it's very abstract, mathematically heavy, very expensive, and difficult to scale in practice. So this is not going to happen in 2 months, okay? But to go to 60 to 90, ladies and gentlemen, now in the last minute and a half, to go from 60 to 90, if the first 70 years were dominated by the tribes working separately and fighting with each other, the future will come from their combination. That's how we're going to manage to have the 7 rings fitting very well on the projects of development on our way to an AGI, to that one ring that rules them all, that hopefully will be explainable, adaptable, flexible, trustworthy, able to extrapolate beyond the training distribution, able to have robust, beautiful, hierarchical, and elegant abstractions, and able to self-improve and adapt to changing environments. And that concludes the presentation. Thank you. Was I in time? Yeah? Great.
Whoa, thank you for firing up the stage, Javier. You were perfectly on time.